Hi guys. So we will solve the first 7 questions of this worksheet, and the rest, the remaining parts, will be solved in the online lecture, online class. Okay. So let's start with the first one. Here we have the question. So we will sketch the graphs of the given functions. First, we have 1 plus ln of x minus 2. So we already know the graph of ln of x, right, as in here. Now, first we will sketch this part, ln of x minus 2. So for that, we shift this graph 2 units to the right, okay? Now, here we have this graph then. For example, you can try here 3, x equals to 3. So you will get ln of 1, which will be 0, right? As in here, as you see. So we shifted this graph 2 units to the right, okay? Now, what's the domain of this function? It's the points where x's are greater than 2, right? Now, what do we do to get the graph of this function? We need to shift this one, new graph, 1 unit upwards, okay, to get this one. So what do we have now? For example, for 3, we need to have, what do we need to have? If we plug x equals to 3, we have ln of 1, which is 0. So we need to have 0 plus 1, which is equal to 1. So as you see, we shifted this graph upward 1 unit. So we get at the point 3, we get 1. Okay, again, the domain of this function is still the same with this one. The domain is the points, the domain contains the points where x's are greater than 2. Okay. Now, what about this one? Of course, the range is the same with ln of x, right? You see, it's R. All right, for that one, what do we need to do? We first note that the graph of e to the x. Okay, we know already that from the first week. So to find this one, e to the x minus 2, we need to shift this graph 2 units to the right again. So here we have this graph. What's that? So for example, at the point 2, we have e to the 0. So it should be 1. Okay. So we shifted this this graph to the right, okay? Now, for example, what happens this point? It's shifted here, okay, for 2. And now this function cuts y-axis at this point, e to the minus 2, right? When you plug x equals to 0, you will get e to the minus 2. So now its y-axis is cut at this point, okay? Now, what do we need to do? We need to find this one. It means we need to shift this graph 3 units now, upwards again. So here we have, again, at the point 2, we need to have 1 plus 3, which will be 4, okay? So for example, that point, again, we shifted this point 3 units upwards, so it will be 3 plus e to the minus 2, okay? The domain of this function is, again, real numbers, right? All real numbers, and its graph is now its range is now, again, the same with the previous one, with the e to the x, okay? So it's 0, it's not included, and all positive real numbers, okay? So what about this function? Now we will rewrite this one because it's hard to sketch the graph of this function. So let's rewrite this function as in this form. We know this inside function can be written as x minus 1 to the 1 over 3. So we can write that 1 over 3, that power, here as a multiple. So we have 2 over 3 ln of x minus 1. Okay, so what do we have? Again, we start with the graph of ln of x. Okay, so what do we do now? We need to first find the ln of x minus 1. So for that, we need to shift the graph of this function 1 unit to the right. So here we have this function. Now, the domain of this function is, of course, x is greater than 1, right? 1 is not included, of course. So now what do we do to find this one's graph? We need to compress this graph by 3 factors, by a factor of 3, and stretch this graph again by a factor of 2. Okay, because we first multiply it, you might think like that. We first multiply it by 1/3. It means we need to compress the graph. Then we multiply it by 2. Okay, and it means stretch the graph. So here we have this function. We cannot say the difference without noting these points, of course. So for example, ln of x at x equals to 3, it gets the value ln of 3, and ln of x minus 1 at x equals to 3, it gets the point ln of 2. It was ln of 3 at the first, and ln of 2 now. Now what do we have at the point x equals to 3? We have 2/3 ln of 2. Okay. Now we have this one. Here we have 2 cosinus of x minus pi/2 plus 1. Okay, let's sketch first this one, cosinus x minus pi/2. Okay, so we already know the graph of cosinus from the first week again. Now to find this part only, cosinus x minus pi/2, we need to shift this one's graph pi/2 units to the right. Now what do we have? We have this graph. So for example, let's examine it a little bit. So for example, at pi/2, we had before the point, we get the value 0 before. Now what do we have? We have, if you plug here, we have cosinus pi/2 minus pi/2, which gives cosinus 0, which is equal to 1, right? So as you see here, we have at pi/2, we have 1. And what about this? We have at pi the value -1. Now, if you plug x equals to pi, you will get cosinus pi/2, which is equal to 0. So as you see here, we have 0. Now, what do? We need to find this part now. Okay, 2 times this function. So we need to stretch this graph by a factor 2, right, vertically, of course. So we have, so you may say that each value in the range of this function, we multiply them by 2. Okay, so we need to stretch it by a factor of 2. Okay, so for example, for pi/2, we have 2, right? We had before 1. Now we multiply it by 2. We have 2. And before we had -1 here, and now we have -2. Okay. Now we need to find this part. It means we need to shift this graph 1 unit upwards as we have +1. If we had -1, then we need to shift this one unit downwards. Okay. So upwards, we will get this graph. Okay. We add each value 1. So we have this graph. Okay. Now the graph of cosinus was, the range of cosinus was -1, 1, including both boundaries, -1 and 1. Now what do we have? We have -1, 3, both included, right? As the range of this function. All right, and the domains are the same. They both they are real numbers. Okay. All right. So we will solve now this one, second part. So we will use this graph to find these values. Okay. So what about this? For example, limit of f when x is approaching 2 negative. So it means we need to approach 2 from left. So here we have so here we have the coordinates. Okay, so we have 2 here. We approach this 2 from left. So on the graph, when we are approaching this 2, on the graph, we find which value? This one. So it is 3, right? So this is 3. Okay, now what do we do for B? We now approach 2 from right. Okay, so on the graph, when we're approaching 2 from the right, we get this value, which is here 1. As they are different, the limit does not exist, we say. Okay, if they were equal to each other, then the limit would be that. But now it does not exist. Okay, what about f of 2? It's here we have the dot. This one is empty. We have this dot, full dot. So it's this one, which is again 3. Okay, what about this? Now we need to approach 4, okay, from left and right, and we need to check if they are equal or not. So we're approaching 4 from right first, and here we see this point, which is 4. So limit of f when we're approaching from right to 4, it's 4, right? And from left, as you see, if we're approaching from left, we get again 4. They are equal, then the limit is 4. What about the value of the function at that point, at 4? We see we have an empty dot, so the function is not defined on that point, okay? And here we say it's not defined. Okay, these are different things. Okay, the limit may exist or not, and a value of a function can be defined or not. Okay, they are different. Okay, now for this question, here we have this one. Now we will sketch the graph of this piecewise defined function. Okay, so let's start with the first one. So when x is less than 0, it's defined by this 1 plus sinus x. So let's first sketch the graph of sinus. Okay. So when x is less than 0, we need to sketch first sinus of x, then we need to shift it 1 unit upward. Okay, so we know when x equals to 0, sinus is 0. As we don't have equality there, we have this empty dot, okay, at 0. Now, for example, when we have minus pi over 2, we know at minus pi over 2, the value of sinus at there is, what's that? Let me sketch that. It's minus 1. Okay, so we have this then. As you know, it's periodic, so we can sketch it like that directly. What are these points, for example? This is minus pi. Okay, at minus pi, sinus gets the value 0. And what about this? This is minus 3 pi over 2. Okay, it gets 1 there. Now what do? We need to shift this 1 unit upward. So it means this one should be shifted 1 unit upward. Okay, so it should be like this, right? So exactly as in here, okay, we have now, for now, this empty dot, okay? Now, what about this cosinus 0? If we plug x equals to 0, cosinus 0 is equal to 1. So we have now this dot, okay? And we sketched the graph of cosinus here, as you all know. And when x is greater than pi, again, you know the graph of sinus, or at least you should know that, okay? And this is the graph of sinus. Okay, now we need to check that if the limit of f, for which values the limit of f does not exist, okay? Let's raise it first. Now, okay. All right, so it's enough to check only these boundaries, okay? Because otherwise the functions are continuous, as you see. Okay, they will have limits at any point in these intervals. Okay, so let's check first this one. So when we're approaching 0 from left, we see it's 1, and from right it's again 1. It's approaching 1, so the limit exists there and it's equal to 1. Okay. And the function is continuous because its value is already, again, the same with its limit, it's 1. So the function is continuous and its limit is 1, okay? And the other boundary is pi, when x equals to pi. From left, we see that the graph of the function approaches -1, okay? So from left, limits when we're approaching pi from left, f of x is equal to -1. And from right, as you see, it's 0 plus f of x. It's 0, they are not equal, so the limit does not exist there. So at the point pi, x equals to pi, the limit does not exist, okay? As I said before, we don't need to check the other values, okay? All right, now for the other question, the problem 4, we will find the limits if they exist, okay? So first we need to check the limit of this function when we are approaching -4, okay? So first we rewrite this one, this numerator, okay? We multiply this one by x and this one by 4, so we have x plus 4 over 4x over 4 plus x, as in here. Okay, so what do we have now? We multiply them and get 1 over 4x, and now we can plug -4 as it's defined, the function is defined, so we get this one. Here at the beginning, we cannot plug x equals to -4, as here in the denominator, we would have 0, right? So we have this one. Now for this limit, what do? We multiply it by its conjugate. So it means the same term with this one, but the sign is its sign is changing with plus. So here we multiply its conjugate and divide it again, because we need to have the same limit, okay? We cannot change it because we write equality there. So for example, if you simplify them, you will get the same limit, okay? So now for numerator, we multiply them first, and you will get this one. And in the denominator, we have the same thing. So in the numerator, as you see, we have 2x, okay? And in the denominator, we have the same again. Now, what do we have? We simplify these x's and we get this one. Okay. Now, you see, we can plug x equals to 0. I forgot again. We cannot plug x equals to 0 here, right? That's why we do whole thing. So what do we have now? We plug x equals to 0. So we get here 2 we had before. And here in the denominator, we will get again 2. So we have 1 as the limit of the function. Okay. Now we have this limit. So if you check first the limit when x is approaching 0 from the left, you see here 1 over x is approaching minus infinity because you're approaching x from left. So remember the graph of this function, for example, if you have problem with that. So when you're approaching 0 from left, you see, this is the graph of 1 over x. You see the graph of the function is approaching minus infinity. So this is minus infinity and this is 1. So we will get minus infinity. Okay, we cannot separate, as here I mentioned that, we cannot separate these limits into two. Okay, we cannot write limit of 1 over x minus limit of 1 over x squared plus 1. We cannot do that because this does not exist. By that, we mean it's not equal to some real number. Okay, so we cannot separate them unless we know they both exist and they are equal. By exist, we mean they are equal to some real numbers. Okay, so this is minus infinity. And from right, here you see from right, it's approaching plus infinity. And still we have 1 here. So the limit is infinity. And you see they are not equal. This was enough. Or we don't have to compute that part because we had already infinity there. It's enough to say the limit does not exist. But if you see, again, we have there infinity. So one of them can be written only. So the limit does not exist. All right. Now, so here we have 1 over x plus h squared minus 1 over x squared over h, okay, when h is approaching 0. Now, again, we multiply this one by x squared and this one by x plus h squared. So we have this numerator over the same denominators, okay? So if we rewrite this one, we will get the same thing, okay? So we have x squared minus, we just write this expansion, okay, over x plus h squared, x squared times h, okay? We just write this expansion, okay? Now what do we have? Here we can simplify them, right? They're canceled out. So what do we have in the parentheses of h? We have minus 2x minus h, okay? Now, if we simplify these h's, we will get minus 2x minus h over this denominator, right? We simplified this h and h in the numerator and denominator. So we have this. Now, if you plug h equals to 0, you will get minus 2x over x squared times x squared. We will have x to the 4th, okay? And we simplify them and get minus 2 over x cubed. So as you see, the limit is taken with respect to h, okay? So here x can be seen as a constant, okay? That's why we can find the limit in terms of x. All right, for this question, we will use Qui's theorem, okay? So let me remind you first the theorem. So the assumptions are as follows. So we have three functions, f, g, and h with this condition, okay? For any value of x, the values of f are less than or equal to g, and the values of g are less than or equal to h, okay? And we have this assumption also, this one. So the limit of f and the limit of h are equal to each other, Okay, so if you have three functions with this condition and this one, so such condition, if you have such functions with this condition, you will arrive that, you will obtain that, or you can conclude by the theorem that the limit of g, the limit in the middle, the limit of the function in the middle is the same with these ones. Okay, so we're given this function, we will find its limit. We want to say that its limit is equal to 0. So if we want to apply this theorem, we need to find two functions, f and h. So here we can see this function as g, right? Because we want to say it's, we want to mention about its limit. Okay, we want to conclude this one. We want to say that limit of this function is equal to 0. So here L should be equal to 0. Okay, so we need to find two functions, f and h, whose limits are the same. They are equal to, they should be equal to 0. Okay, so we will use this inequality. Okay, we know for any theta in real numbers, sinus is in between -1 and 1. Recall that the graph of the function sinus, we already said in the first week that the range of sinus is in between -1 and 1. So we have this already. All right, now what do we have? We want to mention about this function, so we need to use that to obtain this one. So if we plug as it's valid for any theta, instead of theta, we can write pi over x. So we have this one, okay? Now, so we need to have this one, we need to have this function. So here I wrote f, but we mean g actually. Let's write it as g to be clear. Okay, this is g. We need to obtain this one's limit. So if we multiply this by the square root of x cubed plus x squared, we will get this function, right? So we multiply this inequality by this one, okay, by this root. We know this root is always greater than or equal to 0, so the inequality holds again. Now what do we have? We have minus square root of x cubed plus x squared less than or equal to g of x, and less than or equal to square root of x cubed plus x squared. We just multiplied this inequality by this root, okay, square root. Now, you see that the limit of this function minus square root of theta and this function's limit are the same and they are equal to 0. So now this one is f and this one is h, as in the theorem. So the assumptions in the theorem holds, right? So we have this inequality, okay, this holds, and we have this equality, okay, this holds. Then we can use the theorem as we have the assumptions. So what does it say? It says that the limit of this function g, here let's say g, the limit of this function is 0, which was the desired conclusion, right? We wanted to show that equality. So we're done, okay? Using the theorem, we prove that the limit of this function is equal to 0. Okay, and now again, we will find the limits. So first, we have this function 2x minus 1 over the absolute value of 2x cubed minus x squared. Let me rewrite again. Okay, and x is approaching 1 over 2. Okay, now first we check left hand side of this limit and then right. So no, first right, then left. Sorry. Why do we do that? Because when we have here in the denominator, when we have absolute values, we need to first equalize them to 0, okay, to see if there are points which makes this this absolute value equal to 0, okay. So if it's equal to 0, then we have 2x minus 1 times x squared equals to 0. So here you see x equals to 1 over 2 makes this function, this denominator, sorry, 0. So we need to check that, okay? Now, when we're approaching from right, what happens? Here we rewrite this denominator, okay? So this is always greater than 0, so we can rewrite it without using the absolute value. Okay, and what about this one? So we have 2x minus 1 in the absolute value. When we're approaching 1 over 2 from right, we plug here x's, some values greater than 1 over 2. So the inside of this absolute value will be greater than 0. So it means we can write this absolute value again without using it, the absolute value. So we have this now. So we can simplify them and we get 1 over x squared. So if we plug 1 over 2 instead of x, we write 4. We get 4. Okay. Now for that one, we have the same equalities. Now we're approaching 1 over 2 from left. So this is always greater than 0. So we can write it outside of the absolute value. Now this is less than 0, right? The values of x are less than 1 over 2. So this will be negative. So we can multiply it by negative and write it without absolute value. So we have 1 minus 2x. If we simplify then, we get minus 1 over, we don't have that. We get here, because you can write it as in this form, right? So we simplify them. We have minus 1 over x squared. Again, we plug 1 over 2 there. So we get minus 4. So as you see, we get different values. So the limit does not exist. Okay. Now, what about this? Again, you see here x equals to 0 is a root of this absolute in this denominator. So we need to examine both. So from right, we have positive values inside, so we can write outside that that absolute value. So we have 0 there, okay, as the inside function is 0, the limit is 0. Now, what about this? We need to multiply it by minus 1. So we have 1 over x plus 1 over x. So we get 2 over x. Now, if we try to plug 0, we see that this function is approaching again minus infinity. The same with the function 1 over x, right? So instead of 1 over x, this has, they look like the same. But as we can sketch the graph of this function by stretching the graph of 1 over x by a factor of 2, right? So, but the limit is the same, minus infinity. So the limit of this this function does not exist, we say. All right, let's stop here, okay? So we will continue this worksheet from this question 7, okay? Okay, we will do all of them in the online class, okay? But if you have any question from the first 6 questions, we can start with them, okay? All right, so see you next week then.